Okay, we have a square ABCD on which there are 4 points taken, one on each side. So we'll come to those notations in a while. Now, this EFGH is also a square. So this EFGH is taken in such a way that that will make a square. So there should be a symmetry about it. Don't overanalyze these kind of things. And whose area is given as a proportion of the entire area. Great. And the CG is longer than EB. So this will help me to, relatively place the points. So first, let me, draw the ABCD any which way. So let us say this is the ABCD. This one doesn't matter. I can name it as I want. Okay. Now it says CG is longer than EB. So what I'm going to do is I'm going to find where G is. So this point G is lying on CD, right? So G is on CD and CG should be longer. So what I'm going to do is I don't want to place this exactly, but I'll just place this G a little closer to D so that CG can be longer because this will be symmetrically happening. So once that happens, so you can have this, automatically you can find the other ones relatively. So just think about rotating this figure. So if you rotate this figure, you'll automatically understand that there should be a point relatively here, a point relatively here. Let me put this a little wider here. Just 1 second. Put it here and let's say here. It doesn't matter, just trying to show the diagram in a way that you understand properly. So that's it. So now let me first build the square. So let me connect these. So this is what we have. And now let us quickly take the points, the names down. So if I do take the names down, so we have E on AB. So this should be E. And I think then they're cyclically, right? Yeah. So this is F, G, and H. Great. Now, because this is the entire thing is a square, and it's proportionately dividing in these parts. So if I claim that this length is X and this length is Y, then proportionately everything should be, symmetrically rather, not proportionately. Symmetrically, everything here should be this divided into X and Y and stuff. So this is Y, this is X, and everything, right? So these are the X and Y's on each side. Because I hope you understand. First of all, the entire figure is a square, so every side should be actually X plus Y, and also that because the inner part is also symmetrically distributing, so every part should be divided into X and Y. So this is what we have. Now, also that let us consider that this length. So if you have seen the proof of Pythagoras theorem, so this figure should be looking a bit similar to you, or something familiar to you. So let me name the side of the square, the inner square, as Z. So let's say these are Z's. So this is Z, Z, and Z. So these are Z's here. Okay. Now, if you take any one of these, so let me just mark this. So let me consider this green triangle here. So this is a right angle triangle, right? So if you consider this right angle triangle, you have the two perpendicular sides as X and Y, and the hypotenuse is Z, right? So that is what we have. So we have something like X square plus Y square is equal to Z square. So this is the one relation that we have. And the other part is that the relationship between the, areas of these two squares. So we know that the area of the smaller square is 62.5%, which is 5 by 8 of the area of the larger square, right? So what we have is something like this. Let me just write it here. Z square, that is the area of the smaller square, upon X plus Y whole square, which is the side of the bigger square is X plus Y, right? So X plus Y whole square, this is equal to 5 by 8. So this is what we have. Now, these are the two information that I have. So I'm trying to find this as easily as possible. I can evaluate form equations and solve, but I want to evaluate this as smartly as possible, so that takes less amount of time. So think about this. I mean, in the denominator of this ratio, you have this x plus y whole square, right? Which is nothing but x square plus y square plus 2xy. And we know that x square plus y square is equal to z square, because right angle triangle, right? So when I expand that denominator, I will get something like this. 2xy here is equal to 5 upon 8, isn't it? Now understand this. If I substitute this x square plus y square, so this part if I substitute with z square, so what I have is nothing but another z square here, which is this 5, right? So what I can do is I can write it in this way. So let me take this off. Sorry. So I can just substitute 5 here, right? So now we have a good relationship, because again, what we can do is, so these are all ratio tricks that I'm applying. So I can consider this z square to be 5, and this 2xy to be 3, because this is 5 plus 3 will work out, right? So I can consider the z square to be 5, in which case this denominator has to be 8. So I'm considering this to be 3. But 3 is not a multiple of 2, right? So let me double this. And because of ratio techniques, I can double this also. So I can assume this to be 10, and I can assume this to be 2 into 3, right? So essentially what I have is xy is equal to 3. So I have xy is equal to 3 and z square is equal to 10. So now try to just plug in values here. So x into y is equal to 3 and z square is simply x square plus y square, right? Is equal to 10. So just try to plug in value. If you look at this first relation xy equal to 3, the first thing that should strike you is 1 into 3, right? So if I break this up as 1 into 3, then 1 square plus 3 square is actually equal to 10. So this is satisfying. So x and y should be 1, and I mean x and y taken 1 and 3 should satisfy. And since we are looking for the ratio of the length of EB and CG, I hope you can see that in this diagram, the EB thing is this x and the CG thing is this y, right? So essentially we're looking for x is to y, and because this is the entire thing is a ratio thing. So if I scale up x and y with the same ratio, neither of these relationship is going to take any problem. I mean that won't be a problem with any of these relationships. So simply I can consider x as 1 and y as 3, giving us the ratio of x and y as 1:3. So this particular question is easy to do once you catch these relationships. In our class, I've shown the proof of Pythagoras, but then if you know that this relationship might help you a little bit. But even if you don't know, you should be able to identify those right angle triangles. Once you do that, then the remaining part is the ratio technique, because if you go into solving, this might take a little bit more time to solve. So that's it for this question in terms of solution. Coming to the analysis part, I would say it would take a bit of time. So let's say roughly 2 minutes, because you need to draw the diagram appropriately, name the points perfectly. Those kind of things should happen in order for you to visualize the problem properly. So that might take a bit of time. And then the rest of it, I mean, if you do it properly, still it will take a bit of manipulation. So roughly 2 minutes is ideal for this particular question to solve. And in terms of scanning, I would say you can mark this question for review and do it later. If you are familiar with the Pythagoras proof, so this is completely that. So these 4 triangles clubbed together, if you just trying to help you recap that once again, if you know it. So if you have idea of that Pythagoras proof, so this idea should hit you immediately. So in that case, you can do it in round 1 as well. So depending on your adaptability to this particular problem, so I would say round 1 or round 2. So definitely you can take a choice on this. So that's it for this question. Hope you understood and enjoyed the solution. Thank you.